Well, maybe I'll get started. This class and the previous class is kind of a week of statistical mechanics or thermodynamics. We're looking at problems involving macroscopic ensembles of atoms and molecules, and we're looking at how to solve the properties of those macroscopic ensembles of atoms and molecules using Monte Carlo methods, using random number generation. So last class we looked at the problem of figuring the internal energy of a quantum gas, knowing the temperature of the gas. And in this class, I want to look at the problem of figuring the magnetization and magnetic energy of a ferromagnetic solid, a magnetic solid, again using Monte Carlo methods. So that's basically the plan. I got a few slides to start with, which are sort of introductions, background material on magnetic materials, how magnetic materials, their properties, their characteristics are related to the electron constituents of the atoms in the material. And also a couple of slides to introduce paramagnetic materials and ferromagnetic materials and how we think about those materials. Then I'll move on to the sort of more kind of mathematical or computational method that we use to solve the problem of the ferromagnet. So when we think about the magnetic properties of those materials, we think about those magnetic properties of most materials as arising from the electrons of those materials that make up the atoms of those materials. So those electrons themselves carry, as well as electrical charge, they carry magnetic moments, and those magnetic moments can play a large role, as well as orbital magnetic moments, in the magnetic properties of the material. So when you think about an electron, because of the quantum nature of the electron, the important point is, given a particular axis, say a magnetization axis, the electron's spin and the electron's magnetic moment can either be aligned with that axis or it will be anti-aligned with that axis. So it's either sort of up or down. One important class of materials are called diamagnetic materials. So these materials, typically when the electron shells of the particular atom or atoms, they're completely filled, and that the electrons in the shells are kind of paired off, so that there's an up electron for every down electron. And that's the nature of most diamagnetic materials. On the other hand, paramagnetic materials, generally where you have the atomic shells of the atoms are not completely filled, and you have an unpaired electron. And so that's typically the source of paramagnetic materials. And so those are two fundamental classes of materials, and we're going to start talking about the paramagnetic case. So for a paramagnetic material, as I say, we think of that material as being, magnetically at least, kind of a macroscopic ensemble of many microscopic magnetic dipoles, so many atomic magnetic dipoles. In an ideal paramagnetic material, the way we think of an ideal paramagnetic material is that those magnetic dipoles, those atomic magnetic dipoles, are kind of affected or influenced by an external magnetic field, but those atomic magnetic dipoles really don't interact with one another, don't talk to one another. So that's what we might call an ideal paramagnetic material. In a real paramagnetic material, of course, not only do the individual magnetic dipoles experience the influence of an external magnetic field, but they also talk to one another. They interact with one another. So a real paramagnetic material has interactions between neighboring magnetic dipoles. Now, one special case of that is when the it's my phone. One special case of that is when the interaction is sufficiently strong that the dipoles can align with one another, even in the absence of some external field. And that's what we call ferromagnetism. So a ferromagnet is a paramagnet in which the interaction between the atomic magnetic dipoles is strong, such that they'll align with one another to spontaneously produce macroscopic magnetization. And the famous example of that, is iron. So that in iron, the magnetic dipoles of the iron atoms, they interact with one another, and they can spontaneously align to create a macroscopic magnetization. There's actually another case, you probably know this, paramagnetic materials that we call antiferromagnets. So those are also materials where there's a strong talking or interaction between the neighboring atomic magnetic dipoles. But in that case, the interaction is such that neighbors tend to anti-align with one another. And so you'll get, if you were to look at a region of neighboring atomic magnetic dipoles in any ferromagnet, you see one up, one down, one up, one down, and so on. You see that pattern. So that's what we call a ferromagnet, antiferromagnet. And famous example of that is chromium. So that's an antiferromagnetic material. Antiferromagnetic materials are less common than ferromagnetic materials. Anyway, so you might think of the paramagnetism as kind of this big family of materials, or big class of materials. And within that big family of materials, there is these small little cells. One is the ferromagnetic materials that can spontaneously align. One is the antiferromagnetic materials that can spontaneously anti-align. Okay, so now I'm going to move on to properties of ferromagnetic materials from properties of paramagnetic materials. So the long-range ordering of the atomic magnetic dipoles in a ferromagnetic material, if you have a long-range ordering, so this situation where the tendency for the dipoles to align spreads out macroscopically. Maybe you've got a whole macroscopic region of dipoles that are pointing up, or macroscopic region of dipoles that are pointing down. That would be long-range ordering. That long-range ordering is kind of manifest in two things that we'll talk about. One is the obvious one of a magnetization of that region of iron, so there'll be a internal magnetic field. And the other one is an associated magnetic energy with that region of the material. So that's the consequences of long-range ordering of the atomic magnetic dipoles in a ferromagnet. If you were to raise the temperature of the ferromagnetic material, you're going to influence the balance between the magnetic interactions between the neighboring atoms and the random fluctuations of the orientations of atomic dipoles. And so as you raise the temperature of the ferromagnet, what you'll see to greater or lesser extent is a reduction in the magnetization, a reduction in the magnetic energy. If you lower the temperature, then you get the converse, right? You again change the balance between the tendency for the atoms to align, the dipoles to align with one another, and the counter tendency for, due to thermal fluctuations, random fluctuations, for them to point randomly in different directions. So if you lower the temperature, then you would get a greater magnetization, magnetic energy. For every ferromagnet, for every ferromagnetic material, there's a critical temperature. We call it the Curie temperature. If you're above the critical temperature or Curie temperature, then the random orientation of the dipoles has won out, and there's no net magnetization. If you're below the Curie temperature, then the tendency to align has won out, and you have a net magnetization, macroscopic magnetization of the material. Now, in that latter case, you don't always see a slab of iron with aligned dipoles as having a magnetization, as being a magnet, because of what we call the domain structure of the iron. So inside a large chunk of iron below the Curie temperature are generally macroscopically small domains, microscopically large domains. So that means that macroscopically small means, you know, micron size, maybe tens of micron size. Microscopically large means that they have maybe billions of iron dipoles in them. So they're large in the number of dipoles, they're small in the sort of everyday size scale. Those regions, those domains would have a magnetization. And so they would exhibit a ordering in a given domain, but you tend to get neighboring domains having opposite magnetization. So that overall in the bulk of the material, for the bulk of the material, for a large slab of iron, then the domains orientated in one direction will cancel with the domains orientated in the other direction. And overall you get net magnetization. Although underneath that apparent lack of magnetization is these, you know, many macroscopically small, microscopically large domains that are actually magnetized. The way you would make a permanent magnet is that you would have to heat up and then cool down that magnetic material in an external magnetic field. And you're using the external magnetic field to kind of freeze in the domain alignment in the direction of the external magnetic field. So that's how you would make a permanent magnet. You'd have to take that step of heating up and cooling down in some external field, and then you would get your, you know, your fridge magnet or whatever. Do those things make sense? So I just went through, you know, electrons and magnetic materials, diamagnetism and magnetic materials, and then ferromagnetism, anti-ferromagnetism as examples of paramagnetic materials, and sort of a wordy kind of pictures of the nature of those different materials. Okay. So now I want to get a little bit more quantitative. So I want to describe a model for ferromagnetic materials, and then I want to describe how we can implement the model for the ferromagnetic materials to make calculations of magnetizations, magnetic energies. So the model is called the Ising model. You may well have heard of it. It's a famous model. It goes back to Ernst Ising and, the beginning of the last century. So it's an old model. And it was really this sort of first microscopic model of ferromagnetic materials. And in the model, it says that, that ferromagnetic material is made of little particles that are magnetic dipoles, and those particles interact with one another, but specifically they just interact with their nearest neighbors. So this atomic magnetic dipole just interacts with the neighbors directly around it, and it doesn't interact over large distance scales. It doesn't interact long range. The only way to get long range kind of interactions or long range effects is by the superposition of all these short range interactions sort of spreading across the ferromagnetic material. So the Ising model just has short range interactions between the dipoles, and typically it's assumed that there's some magnetization axis, and the dipole can either align with that axis or anti-align with that axis. So it can either point along or point opposite that axis. And then finally, there's one other thing that I wanted to mention. Can't remember what it was, which means it must have been really important. Anyway, maybe it'll come to me. So there's an equation that we can write down for this interaction between the neighboring dipoles, and it's an equation that just specifies the magnetic energy associated with a pair of neighboring dipoles. And in the Ising model, that magnetic energy between a pair of dipoles has some characteristic size, so some characteristic number of electron volts or joules or whatever, and it has a sign that's dependent on whether the dipoles are aligned with one another or oppositely aligned with one another. So, if you're going to favor the dipoles being aligned with one another, then that's going to have a lower magnetic energy. If you're going to disfavor dipoles being anti-aligned with one another, that's going to have a higher magnetic energy. So you'll favor the lower magnetic energy. That's what goes into the Ising model. So that model can actually be solved exactly in one dimension. And I got on here, it's buried in the middle of this slide. This is the magnetic energy associated with the magnetization for a one-dimensional lattice of magnetic dipoles. So to just picture this, imagine some line, and you placed on the line, equal spacing, a string like Christmas lights, right, of magnetic dipoles. And each dipole interacts with its two neighbors. And each dipole interacts with its two neighbors with some characteristic strength. In that equation, the strength is called epsilon. So epsilon is an interaction energy. If it's bigger, then it's a stronger interaction. If it's smaller, then it's a weaker interaction. So they're interacting, and that interaction creates an overall magnetic energy that's given by this little formula here. So just what are the quantities in it? So, I mean, some of them we recognize. So kT, right, Boltzmann constant times the temperature, that has units of energy too, thermal energy. And actually, in the argument of this function, we're comparing the magnetic energy associated with a pair of interaction dipoles with the thermal energy here. So here you see this fight between thermal fluctuations and magnetic alignment. So that's going on in the argument of this function. Out front of the function, you see a couple of parameters describing the problem. It's not surprising that they're there, right? So the total magnetic energy is in proportion, it says, to the interaction energy between a pair of dipoles, which probably just makes sense, right? If you increase that interaction energy between a pair, you'll get an overall larger macroscopic energy, and vice versa. It's also in proportion to the number of atoms in your macroscopic ensemble. And that makes sense too, right? If you put in twice as many atoms, you can get twice magnetization, and vice versa. So those factors out front make sense. The minus sign is because if you've got a ferromagnet, it wants to align the dipoles, and that's going to produce a lower magnetic energy. So it's a negative magnetic energy. Anti-aligning would produce a positive energy. So this equation is quite informative. I mean, it's nice and simple. We like that. And it's quite informative. We like that. Because it tells us kind of the properties of this one-dimensional array of atoms as a function of the temperature. So that if you can't remember, I would never remember, but tan function, right? If the argument is 0, then the function is 0, and if the argument is large, then the function is 1. So it's basically, as you go from 0 to infinity for the argument, that function goes from 0 to 1. And what you're saying as you go from, so how do you make the argument small? How do you make the argument large? You make the argument small by making the magnetic interaction energy small compared to the thermal energy. So if you do that, the argument will be small and you get no magnetization essentially, or very little magnetization. If you make the argument in the function large, you do that by making the magnetization energy much bigger than the thermal energy. Then you get a large argument, you're going to get the full magnetization. The biggest magnetization you can get is simply that all the dipoles are lined up, and then the magnetic energy is the product of individual energies times the number of atoms. So that's all embedded in this. And in this formula, you see this sort of transition from being magnetized to not magnetized. So if you were at low temperatures, which means small thermal energies, you'd be magnetized. If you're at high temperatures, you'd lose the magnetization. Now, one thing that's different about this equation for the one-dimensional case from the other, the two-dimensional or a three-dimensional case, is that the transition from no magnetization to magnetization is much smoother for this one-dimensional case than it is for the two-dimensional and three-dimensional cases. In the two-dimensional and three-dimensional cases, the transition gets much more kind of a spontaneous thing. Suddenly you're magnetized. That probably makes sense, right? If you think about, well, in one dimension, you've not got many neighbors. This is a more gradual spreading of the long-range influences. In especially three-dimension, you've got a more rapid spreading of the short-range interactions to a long-range ordering. So that's why the phase transition in a second 2 dimensions and 3 dimensions is much more rapid. What else was going to say? Okay, the last thing I wanted to say, so, the one-dimensional case is analytically exactly solvable. The two-dimensional case was solved after 20 years, so that's exactly solvable. The three-dimensional case, as far as I know, has never been solved. So for the Ising model, never been solved sort of exactly. So that's an example where we would need some sort of simulation, some sort of Monte Carlo simulation to look at to calculate the magnetization of a three-dimensional ferromagnet. Also, the calculation for 1- and 2-dimensional ferromagnets, so computational Monte Carlo method, can be very instructive too. Now, just this point that you can't you can't do the calculation by walking through all the microstates of the system and evaluating their energies, magnetic energies, and calculating an average. That doesn't work, because even if you just had a tiny array of atoms, say 2-dimensional array 10 by 10, so 100 atoms, you've got 10 to the 30 macrostates. So you can't do what seems to be an obvious procedure based on Boltzmann factor and the partition function, which is to just take the probability of each microstate, multiply it by the magnetic energy of that microstate by that probability, and then just average them all up. But you've got 10 to the 30 in your average, so it's impossible. So that's where the Monte Carlo method from the last class, we use that Monte Carlo method in this class too. So this is just a slide from the last class. I just wanted to remind you of this Markov Chain Monte Carlo method. So it basically amounts to a way of calculating a macroscopic quantity, like last class it was the internal energy of the gas. In this case, it's also going to be an internal energy we calculate, so magnetic energy, but still an internal energy. Once we get that internal energy, we'll get also it comes with, for free, the microstate. We can calculate the magnetization. But we're going to, like last class, calculating internal energy, we're going to be calculating the magnetic energy. Basically, what you do is you pick some suitable initial microstate. We did that last class, we do that this class. Then you start randomly walking in the space of all the microstates by, in last class, we excited or de-excited a gas atom. In this case, we're flip the spin up to down, down to up of a dipole, magnetic dipole, changing the microstates. You guide that random walk by what's called importance sampling. We don't accept everything. We accept or reject based on the Boltzmann factor. And that's kind of like what is called an importance sampling, is this kind of guidebook towards the macrostate that will describe the system, the microstate for the macrostate that will describe the system. So that's on here, this item 3. When we take our random walk through the microstates of the ferromagnet, we're going to guide that walk through this acceptance rejection of the spin flips in this particular case. And then we just got to do that many, many times, tens of thousands times. So this is how it works this is the implementation of the Markov Chain Monte Carlo method for the Ising model. I'm going to do it in 2 dimensions in my little code here, and you'll do it in 2 dimensions in your assignment. You can do it in 3 dimensions, just we would be sitting here or standing here for a long time while it chugged away in a 3-dimensional space. So we're going to do 2-dimensional case, and we're going to, in that case, we're going to be able to explore, in particular, this phase transition that's present in 2 and 3 dimensions around the Curie temperature between magnetized and non-magnetized. So we'll be able to look at that. So there's some specifics that are written down here about our model. So the model I'm going to show you is where, when I talk about the nearest neighbors in 2 dimensions, imagine this dipole, then my nearest neighbors are going to be the one directly below, the one directly above, the one directly to the left, and the one directly to the right. So there's going to be 4 nearest neighbors. There's other ways you could do that. You could pick, you got 1 here. You could pick, there'd be 3, 3, and 2 more. So that will be 8 near, obviously. 8 nearest neighbors. You could do that too. I mean, that's a perfectly reasonable model. But we're going to do the 4 nearest neighbors. So those 4 nearest neighbors, I wrote them down here. So if my dipole that I'm calculating the magnetic energy of is located in the lattice at coordinates ij, then I plus or minus 1 are the guys to the left and right, and j plus or minus 1 are the guys upstairs and downstairs. So we're going to use those. This is my equation over here on the right. This is my equation for the magnetic energy associated with that interaction. So what am I saying here? I've got a sum. That sum is the sum of the nearest neighbor pairs. So that's a sum over 4 pairs. I've got a product, SI, SJ. SI and SJ are either +1 or -1, depending on whether they're up or they're down. So that product is just going to be a +1 or a -1, depending on whether, what does it sample? It depends whether they're aligned or they're anti-aligned. So if they're aligned, it's going to be 1. If they're anti-aligned, it's -1. J, what's J? J is the characteristic interaction energy. So some number of electron volts, energy, the interaction between 2 neighbors. So that would be different if you had iron or nickel or whatever magnetic material. So that's a characteristic of the magnetic material. Then finally, the minus sign is that we want to make, because we're thinking about ferromagnets, if J is a positive number, then we want to make the alignment, the lower energy state, we need a minus sign. And so that's where all that comes from. One thing about this is simple to write down. If I think of J being measured in the units of KT. So if J is 1, that energy, interaction energy J equals KT, thermal energy. And if it's J is smaller than 1, then magnetic energy is less than thermal energy. If it's bigger than 1, magnetic energy is greater than the thermal energy. So that's just going to kind of clean up the code a little bit, just to work in those units. Cleans up a bit the use of the Boltzmann factors and accepting, declining the steps in the random walk. So when I tailor the Markov Chain Monte Carlo to this problem, the way I did it was I started with a random orientation of magnetic dipoles. I then pick a dipole in that collection. I've got 100 of them, and randomly I pick it. And if it was up, I'm going to flip it down. If it was down, I'm going to flip it up. I'm going to calculate the change in energy of the macroscopic state when that one dipole flips. So the energy may go up, the energy may go down by an amount that determines by the, that sum involving the interaction energies with the nearest neighbors. If it goes down, then I'm just going to accept it, which is sort of the basic rule for this Markov chain for macroscopic ensembles of atoms and molecules. If it goes up, I'm going to test it against the Boltzmann factor to determine whether I accept it or decline it. Because if it's going to go up a lot in energy, I'm going to disfavor that. If it just goes up a little bit of energy, I'm going to probably accept that. And then I just do that many times. Now, if we repeat that many times, remember we sort of had to, on Monday's class, we had to kind of burn in the macro state, equilibrate the macro state, and then once we got equilibrium, we could extract the internal energy. It's exactly the same thing for extracting the magnetic energy. And when you extract the magnetic energy, we've also got the microstate. And if you've got the microstate, if you know which atoms are up or down, really, if you just know how many atoms are up or down, you can calculate the magnetization too. So the magnetization itself comes along for the ride at the end.